Okay, so domains and compositions. So we'll look at mathematical domain and word problems, and then we will look at compositions, and we'll throw in a little bit about arithmetic for functions. So stadium holds 50,000 people. When ticket prices are set at $50 per ticket, they sell 15,000. If they raise the ticket prices by $1, they lose 500 in sales. So number of tickets sold as a linear function of price. And so the idea here is that price determines the number of tickets sold. So we want price as our input and number of tickets sold as our output. And we know if we have $50 as a price, we have 50,000. No, we have 15,000 tickets sold. And if we increase the price by $1, so to 51, then we lose 500 in sales. So that means 14,500. Great. A linear function of price. Well, we've got 2 points here. So slope we know is going to be 15,000 minus 14,500 over 50 minus 51, x1, y1, x2, y2. And that's going to be minus 500, positive 500 over minus 1 is minus 500. And the units here, these units are tickets sold. And the price is in dollars. So tickets sold per dollar. And so increasing the price by $1 means you lose $500 in tickets, right? And so this is a statement about the slope. So we'll call this P, we'll call this T for tickets. So tickets minus 15,000 equals slope, which is minus 500 times price minus 50. This is the point slope form of a line, which we know is y minus y0 equals m, y minus y1 equals mx minus x1. M is minus 500, and I'm going to use P for price. So I'm using P instead of Y. I'm using P instead of X. And then I'm using T instead of Y. Okay, and if you solve that, you get T equals minus 500P plus 40,000, solve it for T. And so we get this equation. The 40,000 is the y-intercept, or the t-intercept in this case, and it tells me that at when the price is 0, right, if you're giving away tickets, 40,000 people would show up for it. So the graph of this would be at 40,000, and then you decrease by 500 every dollar increase in price. And so you would sell nothing when you're at 40,000 over 500, which is, if you set the price to 80. And so this is my P axis for price and my T axis for tickets sold. And there's the equation of the line. So what's the domain of this? Well, it looks like it should be all numbers, but really you can't have negative ticket prices because then you're paying people to actually show up. And if you put your ticket prices bigger than 80, nobody will buy it. So the domain here for the word problem is 0 to 80, or your prices should be between 0 and $80, right? More than 80, nobody shows up. Less than 0, you're giving them away. And that's different from the domain of the formula, right? Which says you could set the price to be any number you want and you could get an appropriate ticket sales. But it's just saying that. But the formula doesn't apply in every case for this word problem. Revenue is price times number of tickets sold. Right? And so if you set the price at $50, you can sell 15,000 tickets, which means your revenue would be 50 times 15,000, which I think is $750,000 in revenue. So here we can rewrite revenue as a function of price, because the price is P, and the number of tickets sold, we actually have a formula for that. That's this, would be minus 500P plus 40,000. And its domain would be the same thing because you can only set P between 0 and 80. And this is actually a parabola, not a line, and we will see more about parabolas as we go forward. And so in general, we have revenue is price times quantity sold, profit is revenue minus cost, break-even points is where profit equals 0, revenue equals cost, and we'll see that coming up in the future. So as we saw in example 1, word problems might specify the domain. We were only interested in ticket prices between 0 and 80. So if you're given a formula in general, not in a word problem, right, what's the actual domain? And these are basically the 3 rules, right? The domain of function is all real numbers except for 3 cases. One is you can't divide by 0. If g of x equals 0, you have to exclude those points. Square roots or even roots in general, right? The thing inside the square root has to be positive, and logarithms, which we'll see later, you have to have positive numbers in that. So domains for this: A, rule 2, you need the thing inside the square root has to be bigger than or equal to 0. So the 2 minus 3x is inside the square root. You solve this for x, you get 2 greater than or equal to 3x, or 2/3 has to be greater than or equal to x. And that means, if you think about the number line, here's 2/3, we want all the numbers less than 2/3. So in interval notation, that would be this. B, that's rule 1. The bad points are where this equals 0. And then you have to factor this. Oh, that's a minus 10. So we need 2 numbers that multiply together to give me minus 10 and add together to give me 3. So there would be x minus, one of them has to be negative because you get a minus sign there. So x minus 2 and x plus 5. 5 times minus 2 is minus 10. 5 minus 2 is 3. Now these 2 numbers are the numbers that make this 0. So f of x, this f of x and b, is undefined when x equals 2 or x equals minus 5, because if you plug those in, then you get 0 in the denominator and something bad happens. So the domain here is, you can write it in 2 different ways. All x except x equals 2, x equals minus 5, or you could write it as minus infinity to minus 5, union minus 5 to 2, union 2 to infinity. I usually go with this because it's a little bit easier than writing it out of those unions. What about C? Well, that involves both rule 1 and rule 2. You need x minus 3 greater than or equal to 0 because that's a thing inside a square root. And so that means I need x bigger than 3. And then rule 2 tells me that I need x minus 5 equals to 0 is a bad point. So x equals 5 is a bad number. I don't want that in my domain because it gives me a 0 in the denominator. So what's my domain going to be then? It's all x greater than or equal to 3 except for x equals 5, or 3 up to 5, union 5 to infinity. And what we've seen here is we're skipping 5. The domain for this, well, there's no division, so rule 1 doesn't apply. There's no square root, so rule 2 doesn't apply. So its domain is everything. So division by 0, square roots, those are a problem for domains. So a little bit about arithmetic for functions. You can add, subtract, multiply, and divide, but you do have to be a little bit careful about domains. So here's two functions. You can tell because of the vertical line test. G of x is this one, the solid line, and f of x is the dotted line. Okay, so there's a bunch of notation here, f plus g of x, f minus g of x, f times g of x, f of g of x. And it's pretty much what you'd think it would be. This is a way of writing f of x plus g of x, and f minus g of x is a way of writing f of x minus g of x, etc. So what's the domains of f plus g of x? Well, you write that as f of x plus g of x. So the domain that can only be numbers that can go in both of them, right? Because if I want to take f of x plus g of x, x has to be in the domain of f, and x has to be in the domain of g. The domain of f is minus 3 to 8. That's my domain of f. My domain of g is minus 4 to 4. So what's the overlap of those two? Well, minus 3 to 4 is the domain. If I take x equals to 6 and try to calculate f of x plus g of x, I can get f of 6, that's minus 2, but there's no g of x because 6 is outside of the domain. Likewise, if I wanted f plus g of x of f of x plus g of x for x equals minus 4, that would work in g of x, but doesn't work in f of x. So the only numbers that work in both at the same time are numbers from minus 3 to 4. And that's the same for f minus g and f times g. We have to be a little bit careful about division. And this is f of x over g of x, because you have to be careful about where is g of x equal to 0. And g of x is equal to 0 minus 2. And that's a bad point because it makes the denominator 0. So domain for f of g of x is, we can go from minus 3 up to 2. We have to skip 2, and then we can go up to 4 because you can't divide by 0. So what's f plus g of minus 3? Well, f of minus 3 is 2, and g of minus 2 is minus 1. So that's 1, right? Not too hard. F over g of minus 3, that means I want f of minus 3 divided by g of minus 3, and that's 2 over minus 1, so that's minus 2. So not too hard to calculate. F minus g of 5 is undefined, right? There's no g of 5. 5 is outside the domain of g, so you can't actually calculate that. Okay, so a little bit about arithmetic of functions, and now composition. So composition of two functions, g followed by f, means to take the outputs from g and use them as inputs for f, and the composition is written either like this, f composed with g, so the circle is read as composed with, or f of g of x. F of x is also called the outside function because it's outside, and g of x is called the inside function because it's inside. And so a picture, if you think about the domain of F, looks like that. It's a bunch of numbers, excuse me. And a function takes you to the range of F. It's a rule that takes you from the domain to the range. And then if this is the domain of G, we end up in the range of G. So we take an X value, we find its F of X value, but now that's a number that can be plugged into G, and so we plug that in there and we get, oh, I got them backwards. This should be G, then this should be F. So this becomes G of X, and then this becomes F of G of X. Okay, so here's two functions. F of X is absolute value of X minus 1 plus 2. G of X is square root of X minus 2. What's F of G of 3? So that means we start with X equal to 3. That's my X value. And then you plug it into F of X to get F of 3. If we plug 3 into here, we get 3 minus 1 is 2. Absolute value of 2 is 2 plus 2, that's 4. And then we take that number and we plug it. Oh, I keep doing things backwards. I'm sorry about that. F of G of 3. Start this again. F of G of 3 means we start with X equal to 3 and we plug it into G of X to get G of 3. This is X. We want to turn it into G of 3. If we plug 3 into this, we get 3 minus 2 inside the square root, which is square root of 1. So we get 1. So that's G. And then F, we get F of G of 3. And so that means I take this 1 and I plug it into this function. 1 minus 1 is 0 plus 2. That gives me 2. So F of G of 3 equals 2. Because I run the 3 through G first, take the output from that, and run that through F. So G of F of minus 8 means we're going to start with minus 8, and then we apply F to the minus 8. And plugging in minus 8 into here would give me minus 8 minus 1 is minus 9. The absolute value of minus 9 is 9, and 9 plus 2 is 11. And then we take G of that, and that means we plug 11 in for X. That's the output there. 11 minus 2 is 9. The square root of 9 is 3. So G of F of minus 8 equals 3. We take the minus 8, we plug it into F, take that output, plug it into G. And then we can look at, well, what are the formulas? F of G of X, that means we take the formula for G of X, which is square root of X minus 2, and we plug it into that. So we want F of square root of X minus 2. And then that means we plug this in for X in that formula, which is absolute value of square root of X minus 2, absolute value plus 2. So there's the formulas. What's the domains and the ranges? Well, looking at this, we just need X bigger than 2, bigger than or equal to 2, right? Because that's the domain of G is every X greater than 2. Domain of F is all reals. Okay. G of F of X equals G of absolute value of X minus 1 plus 2. And that should be square root of absolute value of X minus 1 plus 2, because that's this function, and then minus a 2. So that's absolute value of X minus 1. It's inside a square root, so what does that mean? It means the thing inside has to be positive to be able to take the square root, but absolute value is always greater or equal to 0. Right? And so our domain here is all x, because no matter what x you plug in, you're going to get a positive number inside of that square root. So what's the ranges? The ranges are a little bit trickier to find. You can find them if you graph them on GeoGebra. But this, we know about square root functions. Square root functions, square root of x minus 2, this is a square root function moved to the right 2 units. So this is the graph of g of x equals square root of x minus 2. And if you take the absolute value of this, well, the y values are all positive, so nothing much happens. And then you add 2, so you just get the same graph moved up 2. So the range is going to be y greater than or equal to 2. For g of f of x, we know the y value is always going to be positive because the range of square root is always positive. This will be at its smallest when x equals 1. That'll give me y equals 0 because the absolute value of 1 minus 1 is 0. So we'll actually end up with the range being y greater than or equal to 0. Generally, range is hard to find if you can't graph the function. To find the range of a function, generally pull up GeoGebra and graph it and see what the range looks like. Composition with tables. Here's 2 functions, f of x and g of x. They're just defined by the following tables. We don't know what the formulas are. All we know is that 1 for f, 1 goes to minus 1, 2 goes to 2, 3 goes to 1, 4 goes to minus 2, and 5 goes to 1. So what's g of f of 2? So this means we want g of f of 2. That means we want to take 2 and plug it into f. And that gives me 2. And then we take that 2 and we look where it is in the x column for g, and then we want to know what the output is. That's 4. What's f composed with g of 1? Well, this means we want to start with x equals 1 and do g first. So that's that. And that takes me to 5. And then I want to do f. So then we'll go back to the x column for f and see what the output is, and it's 1. F composed with f of 5, well, that means you start at x equals 5 for f, and that takes you to 1. And then we want to put that back into f, and that takes us up to 1 as the x. So we take the output here, plug it in as x, and that gives me an output of minus 1. F composed with g of minus 1, well, g goes to takes minus 1 to 1 to minus 1, and then we find out that minus 1 is not one of the available options. So that's undefined, right? Because g takes minus 1 to 1, minus 1, but then there's no place to put minus 1 into f of x. And so that happens. So we can put together compositions, right? G composed with f of x, that means we're going to start with x and find f of x, and then we'll take that output and put it in here. So if we take our domains 1, 2, 3, 4, 5, that's the domains for f. 1 goes to minus 1, minus 1 goes to minus 1. 2 goes to 2, and g takes 2 to 4. 3 goes to 1, 1 goes to 5, 4 goes to minus 2 goes to 3, 5 goes to 1, 1 goes to 5. So this is a table for g composed with f of x. If we try to do the same thing for g first, we actually have to use the x's that are in the domain of g. And so that's going to be minus 2, minus 1, 0, 1, 2. We take these, we plug them into g first, and then into f. So minus 2 goes to 3, and then 3 goes to 1, so it's okay. Minus 1 goes to minus 1, and as we notice above, undefined. 0 goes to 4, 4 goes to 2, 1 goes to 5, 5 goes to 1, and then 2 goes to 4, and then we plug that into F, and that gives us 2. So the table for F composed with G of X, if you insist that everything in the domain of G has to go somewhere, you can't do that because you have an undefined thing. If you're willing to drop minus 1, you can get a function that's defined for minus 2, 0, 1, and 2, but you have to drop the minus 1, which can be annoying sometimes. So decomposition, complicated functions can be created by plugging other functions into other functions, right? So if I look at this, if f of x is a composition of two functions, I need an inside function and an outside function. And the inside function is usually easy to find because you have nice parentheses or something. So here we have the absolute value bars. That tells me that my inside function is x squared plus 3x plus 2. So what's the outside function? What do you do to this x squared plus 3x plus 2? Well, you take the absolute value of it, right? And so as a check, f of g of x would mean take this expression and plug it in for x in this expression. And that gives me the function that I want. And likewise for this function, my inside function, if I want to write g of x as a composition, my inside function is the thing inside the square root. And what do I do to that function, right? So I take my x squared plus 2x plus 5, and what do I do to that? Well, I just take the square root of it, square root of x. And again, that tells me that f of g of x, that means take this whole thing and plug it in for the x there. That allows me to find in the inside and outside functions. And this one, H, is actually a little bit trickier because we can also think about these things as a sequence of things, right? We could say we start with X, and then what do we do with it? We subtract 2 from it, and then we take the square root of it, and then we put it in the denominator. So 3 steps. And these are all functions. And what are the functions? We'll call them F and G and H. So F is actually pretty easy to see. It takes X as its input, and it gives you X minus 2 out. But what's the function G? Well, it's taking an input here, which we'll call U. And what does it do to whatever its input is? Well, it gives you a square root. So G takes an input, which we can call U, and it gives you an output, square root of U. So what does H do? Well, this is the input that's going into H. We can call that V. And what does it do to that input? Well, it puts it down in the denominator, like that. So H of V is 1 over V. And we like to actually write everything with x's as the variables. So we could write this as f of x equals x minus 2, g of x equals square root of x, h of x equals 1 over x. And then if we compose these, we take the x minus 2, we put them into this, that gives you square root of x minus 2. Then we take all that and we put it where the x is there, and that gives me this. So this can be a useful way to think about them as a sequence, and you can think about the labels a little bit. If we thought about this in this case, it would take me x goes to x squared plus 2x plus 5. That's this first function. And then the second function takes you to the square root of x squared plus 2x plus 5. And if we call this the input for G, if we just say, well, we're going to call that U, what does G do to this thing, this input? Well, it just takes the square root of it. So f takes x to this, g takes u to square root of u. And that's one way to look at finding the decomposing functions in terms of other functions. So a couple of financial points here, the rules about domains, and some stuff about composition of functions. And that's that.